So we've talked about how to do a hypothesis test for a population proportion in the last notes. In these notes, we're going to talk about a little bit more specific of a test. It's called a two-sided test. And for now, we're still going to be focusing on proportions for this section. So why do they call it a two-sided test? And that actually comes from the hypotheses. We know the null is always an equal sign, but the alternative, that could be either less than, greater than, or not equal to. So the not equal to is key here. That's when we have a two-sided test. So when the alternative hypothesis has a not equal to sign, meaning for the two sides, it's not just the greater than side, it's not just the less than side, it basically will take either one, right? So it takes two sides. So let's take a look at the first example here. It's called Benford's Law and Fraud. It says when the accounting firm AJL and Associates audits a company's financial records for fraud, they often use a test based on Benford's Law. Benford's Law states that the distribution of first digits in many real-life sources of data is not uniform. So for real-life sources of data, that's like your age, your weight, your bank account, your salary, any form of data that we can get from the real world, apparently the first digit, it's not fair, right? It's not like 10% of them are 0, 10% of them are 1, 10% of them are 2, and so on. It says, in fact, when there is no fraud, about 30.1% of the numbers in financial records begin with the digit 1. So that's really not fair. 1 gets 30.1% of the digits as far as being the first digit for that financial record. Maybe it's an expense report. However, if the proportion of first digits that are 1 is significantly different than 0.301 in a random sample of records, AJL and Associates does a much more thorough investigation of the company. So apparently when they say that basically about 30% of expense reports that we get from your company should have 1 as the first digit, they've probably established that number over a really long period of time and over looking at a whole lot of data, right? A whole lot of expense reports from companies. So if they get the expense reports back from a company and they look at the first digit for all the expenses, if they aren't at about 30% as having 1s for their first digit, they're going to be in trouble. That's like setting off an alarm. This firm is probably going to come audit them if they're really far off that mark, right? If they're close to it, then they're probably okay. But that's one thing they use to start to monitor fraud. So it says, suppose that a random sample of 300 expenses from a company's financial records results in only 68 expenses that begin with the digit 1. Should AJL and Associates do a more thorough investigation of this company? And we're going to have to answer that with a hypothesis test. And our sample data in this case would be 68 out of 300. Whatever that proportion is, we can compare it to the desired proportion of 0.301 and start to think, how far off is that? So 4 parts to a hypothesis test question. We know there's 4 steps for the grading rubric. So let's start with the state step. So the state step, we want to test 2 hypotheses, the null and the alternative. The null is like the neutral one, right? The null says everything's okay. The true proportion is equal to 0.301, right? Nobody's cheating, nobody's committing fraud. And then the alternative hypothesis would say, if you're too far off this, I don't care in what direction, whether it's above or below, but if you're too far off this number, we can suspect that you're committing fraud. So the alternative would be the same thing with a not equal to. Okay, so that's half the credit. The only thing that doesn't make sense yet is we haven't said what P is exactly. So we've got to make a statement here. We can say where P is the true proportion of expenses having a 1 as the first digit. And then we need to be just a little bit more specific because we're actually looking at an individual company, wherever they obtain this data from, right? So for whatever this company is. They didn't name it, but for whatever this company is. And then the only other thing we need to mention here is how picky we're going to be, right? When it comes to rejecting or failing to reject, we've got to say what alpha we're going to use. So we'll use the typical one, using alpha equals 0.05 for the significance level. All right, and I just need some room here, so I'm going to go ahead and clear this off. Let's go to the plan step. So one thing that's new for us is we have to name the type of test that we're going to do. So we can say if the conditions are actually met, so if the conditions are met, we'll do a 1 proportion z-test. A 1 proportion z-test. So that's the name of the test that we're going to run. The conditions, the randomness one should be pretty straightforward. I mean, it says it right there in the problem, right? They took a random sample. So we can say it's stated in the problem, check mark. The independence condition, I assume they sampled without replacement when they grabbed those 300 expense reports, so we can just talk about the 10% condition. So I think it's safe to assume that the company being audited, right, the one that they're looking at, has more than whatever 10 times the sample size, in this case 300. So they probably have more than 3,000 expenses. So that means the 10% condition would be met. And there's a check mark. So if it's a big enough company, they're going to have at least 3,000 expenses to speak of, so 10% condition's all good. So independence condition is done. So then the last condition, we just have to say something about normality. And for proportions, you remember it's NP, N1 minus P. Like we can expect 10 successes and 10 failures. We just have to be careful when it's significance test. We're going to use N and then P naught, right? The P that comes from the null hypothesis, which was 0.301. So we know N is 300, and then P naught, the one that comes from the null hypothesis, not P hat, that's 0.301, which if we round it is about 100. So that's good, right? That's at least 10, so that gets a check mark. And we have to show the other way, so N1 minus P naught, so 300 times whatever 1 minus 0.301 is, and that should get us approximately 200, which is also at least 10. So those are both good. So that means the large counts condition is all good. So that means we can assume normality. All right, so we met all 3 conditions. We said what type of test we're going to run. So now it's just time for the do step. So for the do step, if you'll remember, there's 2 things that I need to see. One of them, we have to calculate the test statistic. In this case, that's just going to be a z-score. And then when we get that, we'll use that to get our p-value. So those are the 2 things, the test statistic and the p-value. So the test statistic, it's a z-score. We're going to take our sample data, p-hat, and we're going to see how far it is from the null parameter, right? So p naught. How far is our sample data from basically that 0.301 number? And then the square root, the standard error uses p naught in this case. And then just off to the side here, what was p hat? So if it was 68 out of 300 for the sample data, that's 0.2267. Seems like that sample data is pretty far from the null parameter there, that 0.301 number. So we'll have to see. We might reject and say this company is definitely committing fraud. Let's go ahead and calculate this. So p hat is 0.2267 minus the p naught from the null hypothesis, that's 0.301, and then the square root stuff, so that's 0.301, 0.699, there's 300 for n, and you should be looking at negative 2.806 for this z-score. So that is our test statistic. And now we can use that to get our p-value. So for the p-value, what's the probability we get sample data this extreme? So what's the probability you would get a z-score at negative 2.806 or below, right? Because that's definitely a negative z-score. So we're pretty far away from 0.301. Now we can calculate the probability. All right, so I'm really glad that we proved that normality condition earlier, because now we can just use the normal curve. So I'm going to draw a curve. It's the standard normal curve, meaning this is where all the z-scores come from. So the mean 0, the standard deviation is 1. And I'm going to mark off 2.806, negative 2.806 down here. I'm going to shade below it. So what is that probability? So we've got experience in finding these. We could use a z-chart. We could use the normal CDF command in our calculator. But one thing I want to remind you of from the alternative hypothesis was this is supposed to be a two-sided test, right? It says not equal to. It doesn't just say less than. So the point being, here's one tail, right? Here's one side. If this is a two-sided test, and we know the normal curve is perfectly symmetric, well, that means we also have to account for 2.806 on the positive side. So we've got to account for both of these tails. So that's a really important note I want to make. I see kids forget that all the time. If it's a not equal to, a two-sided test, basically we have to double the p-value. So in other words, I know you got this negative z-score, and we're going to find the area of this tail. And then to get the right answer, you would really just need to double that probability, whatever you get for that answer, right? Double it, that's going to be your p-value. So if you use the normal CDF command, we can say using technology, normal CDF, the lower would be, if I'm just finding this tail right here, negative 1e99 up to negative 2.806. The mean is 0, standard deviation is 1. If you just find that tail, then multiply this answer by 2. And that should give you your p-value of 0.005. One interesting thing that also works here, if it's a two-sided test, and you want to know what the area is under these tails together, I guess you could have just done 1 minus this whole white area, right? If you're really efficient with using normal CDF, you could have just gone negative 2.806 up to positive 2.806. And whatever that answer is, just do 1 minus that. That should get you to the same place in this case. But in general, I don't want you to forget, if it's a two-sided test, the not equal to kind, whatever you get for this p-value, go ahead and double that. All right, so the do steps got full credit. We got the test statistic right here. We got the p-value. Last thing on the agenda for this is the conclude step. So our p-value is definitely really, really small, meaning it's way below our alpha level. We're going to go ahead and reject, right? So we have to mention why we're rejecting it. Because our p-value of 0.005 is less than our alpha level of 0.05, we reject the null hypothesis. This would only get half credit, though, because it doesn't really tell us what we're concluding in the context of the problem, right? So which one do we support? Do we support the null or do we support the alternative? Well, if we rejected the null, right, apparently we support the alternative. So we need to say that in context. So we do have convincing evidence, right? We rejected the null, so apparently we support the alternative. We have convincing evidence that the expenses at this company do not follow Benford's law, right? It's pretty much too far off of this 0.301 number for us to trust it. In other words, they should be audited or investigated further. So you need to have a statement like this. We have convincing evidence or we don't have convincing evidence. And you need to say what that means in the context of the problem. And then along with this statement, where you reject or fail to reject based on your p-value as it compares to alpha, you would get full credit for the conclude step. All right, and then I'm just going to scroll down here to the part where it says describe a type 1 and a type 2 error in this context. So context being the key word here. I see a lot of people just say reject the null, fail to reject the null, and you won't get credit that way. So we need to make sure we're talking about it in terms of the problem. So a type 1 error, I know that means you rejected when you shouldn't have, right? So in other words, a type 1 error would be concluding that the company should be investigated. And apparently, you were wrong. You did that by mistake. So concluding that the company should be investigated, when in reality, they're actually not doing anything wrong, right? When in reality, their records aren't fraudulent. So that's one error we could make in our conclusions. And remember, a type 2, that's fail to reject. So how would this look if we failed to reject and made an error? Well, that would be like not concluding that they were committing fraud, right? So not concluding that the company should be investigated. When in reality, they are committing fraud right and left, right? So when they've committed fraud. This one, in terms of this problem, this would definitely be the more offensive error to make, right? This one, like, not quite as big of a deal because, so what, you have to audit a few more companies, and yeah, I know it's a hassle, but it's for a good cause, kind of. Type 2, well, you let some fraud go unnoticed, and then some companies commit fraud and continue to commit fraud. So you really wouldn't want to make a type 2 error for this example. So up top here on the next page, it says, can you use confidence intervals to decide between two hypotheses? The answer is actually yes. They're kind of nice. It says, what is an advantage to using confidence intervals for this purpose? Why don't we always use confidence intervals? So let's start with an advantage for using confidence intervals. In general, they give more info. And how do they do that? Well, because they give you a range of plausible values, right? They're like, oh, the true P could be from here to here, for example. So they give you more info in that way. Can you use them if you're comparing hypotheses? Yeah, but confidence intervals will only match with that two-sided hypothesis test, right? Confidence intervals will only match the two-sided one. It can't do just greater than or just less than. So it can only do the symmetric one, the not equal to kind. And then what's kind of the difference? Why don't we always use confidence intervals instead of just hypothesis testing? Well, the standard errors are slightly different, right? That square root thing with the p's underneath it. So for confidence intervals, if you remember, they just took some sample data, p hat, and they used it to build an interval. So the standard error of p hat, the square root used just p hats. For hypothesis tests, they start out by assuming that the null hypothesis is true. That's kind of important. So a hypothesis test starts out by assuming the null is true, so it uses the p from the null hypothesis, aka p naught. So there is just a little bit of difference when it comes to the standard error parts. But let's look at the Binford's Law one, example 2. So a 95% confidence interval for the true proportion of expenses that begin with the digit 1 for the company in the previous alternate example is 0.180 up to 0.274. That's their confidence interval. Does the interval provide convincing evidence that the company should be investigated for fraud? One thing I want to point out really quick, in the first example, when we did the test, alpha was 0.05. Now when we do a confidence interval for this one, the confidence level is set at 95%. So there's an interesting relationship there, right? Alpha was 0.05, this is 95%. If this was 99%, you could probably guess what alpha would be. Anyway, does this interval give us convincing evidence that basically they're committing fraud, or at least they should be investigated further? Heck yeah, it does. Right? You'll notice there's a really important value that's not on there. If you remember Benford's law from the first example, and that's 0.301, right? So since 0.301 is not on the interval, right? Here's the interval. We can say that that value is not one of the plausible values for p. So that's kind of the key here. Let's see, 0.301, not on the interval, not even close, in fact. So it doesn't look like we can consider it to be a plausible value. Even if it was in there by just a hair, I would say okay, but it's not on there. Which means if it's not a plausible value, that means our statistical opinion says this company should be audited or investigated further. All right, so we've done our first two-sided tests. We talked about Benford's law. That's kind of a cool and interesting theory. We related confidence intervals to a two-sided test a little bit with this example. And one thing I really don't want you to forget, if it's a two-sided test, you've got to take the p-value, whatever you calculate it as, and double it. Right? So be really careful with that. That's kind of the big takeaway here from these notes. Which I think we've about covered everything so far. So that will be all for these notes. I'll see you in class.